Welcome to another video tutorial, the first one of 2020. So in this video, I will be talking about machine learning model matrix, right? So how to measure whether the model that you have just trained has learned the correct relationship between your target variables and your feature space. So I'm gonna limit the video to just two, to classification and regression. Clustering is another topic entirely on its own. So yeah, for today, I'm just going to be focusing on classification and regression. So yeah, let's get to it. So classification, right? Um, okay, the reason I'm creating this video before I actually start doing deep diving on the theories for classification and regression for machine learning, it's because the guys that have been following my videos, a few of them contacted me asking me about like, okay, cool, I see what you're trying to say here, but like I've trained my model and then I've submitted on Zindi on the platform, and then I'm getting a 0.8. Is that a good thing or a bad thing, right? So yeah, I'm just gonna be like trying to touch on that with this video, trying to address that actually. So when you're dealing with classification, generally it would be for categorical variables, right? So what are categorical variables? Categorical variables are like your discrete values, like it's either it's this or not. For example, color, right? So it's either the color of your hair is black or not, or like it's another color, right? But it has to have a color, right? So days of the week, it's either Monday or it's Tuesday or Wednesday. Animals, I think you this one, it's a classic application for image classification, dog or cats. So number 5 is binary, right? Either yes or no. So cat or dogs, it's a very popular application for your convolutional neural nets, where like you train a model to classify like whether this is a dog or a cat. I don't know why people do that. No, I'm just kidding. It's a cool application to like get into the application of image classification. So yeah. So under classification, I will be focusing on like three topics, right? The first topic would be confusion matrix, just to make sure that I clear off all the confusion. Excuse the pun, but yeah, the first one is going to be confusion matrix. The second one we'll be talking about accuracy, right? And then you'll see why I don't recommend accuracy for when you're doing classification, particularly for your binary, but like you'll see. And then the classification report, right? This is classification report has everything that you need to diagnose like or to evaluate your model. So yeah, let's get down to it. In order to make this more practical, I've created a sample data, right? So from this point, say we have trained a classification model. So what this model does, it takes a certain number of features, and then it predicts whether this patient has cancer or not. 0 for no cancer, and then 1 for cancer, right? You can see here, this patient doesn't have cancer, this patient doesn't have cancer, this patient doesn't have cancer, but this patient has cancer. And then the same for all these ones, they don't have cancer, but this one has cancer. So out of 10 in my sample data, there's 2 patients that have cancer, right? This is the actuals. Now what my model predicted was that out of the 10, all 10 of them don't have cancer. So we will take the actuals and the predictions to just calculate the matrix to see. Okay, let me start off by importing my stuff over there. I just want to be able to display images, my sample data. Let me run that, and then here what I did was I took this and then I made it a yes and no. Like the zeros would be no, this person doesn't have cancer. The ones would be yes, this person has cancer, same as that one and that one, so that it's easier to visualize in the classification report. So yeah, let's start with confusion matrix. What you're looking at here, you have it's a matrix, right? A 2 by 2 matrix. So your columns would be your actuals, and your rows would be your predicted values. So the ones that are highlighted in red, these are the most important ones that you want to make sure that you optimize for. So here we have actual positives, and then here we have predicted positives. So this would be your true positives, right? So to say that, so in this case, the positive case would be no cancer. The negative case would be yes, the person has cancer, right? So following along that line of thought, so the negatives, the actual negatives and the predicted negatives would be here. So since we have two cases where there's two patients with cancers, we expect to see 2 here and then an 8 there. So those are the true positives. I predicted that this person doesn't have cancer and they don't have cancer. I've predicted that this person has cancer and they have cancer, right? So the false positives would be where you predicted that this person doesn't have cancer, but they actually do have, no, false, yeah, false positive. So they actually do have, right? And then your false negatives, the actual would be positive and then the predicted would be negative. So it will be a false negative. I'll visualize it in the next cells. So what you need to do to start using the confusion matrix, because scikit-learn has in a built-in function for that. So you would just like call it off the matrix, import confusion matrix, and then this is how you would put in your features, I mean your data into the confusion matrix function, right? So you start with the actual and then the predictions. So it's going to compare between, you always start with the actual and then the predictions follow. So right, you can see this is the confusion matrix that scikit-learn or Python would spit off. So for the true positives we have 8. So we have 8 cases of no cancer, and then for the true negatives we had 2 cases of yes cancer, but our model said no, so we missed out on, we got 2 wrong there, right? So what you wanted, ideally what you want to have is 8 there and then 2 here, ideally. So that would be, your 100% accuracy. But like whenever you get 100% accuracy, just know that your model is wrong. Just go back, you did something wrong, right? Cool. Speaking of accuracy, you would import it off of matrix as well, and then accuracy score. So and then the way you call it the same way you called it your confusion matrix, right? You would put in your actual and your predictions in there, so our yeses and nos in there. So you see it's 0.8, right? So out of 10 cases of that we predicted that they don't have cancer, 8 had cancer, so we get 8 correct. So that's your accuracy, 80%, right? So now this is where it gets a little bit dangerous in the case of using accuracy for classification, right? Say that this model is in production, and what we're doing is we're streaming in data of patients, right? So we want to be able to predict whether this person has cancer or not before we go into like the deep blood work. So right off that, we feed it the data, so the model would have an 80% accuracy, which doesn't sound that bad, right? 80% of the time it's accurate, but 80% of the time it's accurate in telling you which people don't have cancer. But you want this model to be able to identify those cases when a person has cancer so that you can focus on that case. Now you can go for the blood works and then, just to catch the cancer probably at an early stage if you're using this approach. Say maybe that was the application of this model. So 80% of the time it will tell you the person doesn't have cancer. And it would be true, I mean, it would be true 80% of the time whenever it tells you that this person doesn't have cancer, but it doesn't tell you when people have cancer. So that's why it's dangerous to use accuracy for binary classification if your focus is the negative cases, in this case where there is cancer. So like you would learn later on in how to how to balance that off, like tuning the parameters of your model to focus more on the negative cases and ignore all the positive cases, right? So now, like I said, classification report is the OG of classification. From classification report, what you get is your precision. Your precision would be the total number of true positives. Say this person doesn't have cancer, over two positives plus two negatives. So all the ones that I got right, whether it's this person doesn't have cancer or this person has cancer. So then you would calculate the precision, and then you would get a percentage for that. Recall would be your true positives, right? The ones where there's no cancer over the ones where there's no cancer plus your false negatives, right? The false negatives are these ones, right? So I predicted that this person has cancer, but they actually don't have cancer. So those cases, this is the formula for that. And then this would be the most important metric that you're going to use whether you're diagnosing your classification model, right? So after calculating all of that, it'll multiply precision times recall over precision plus recall multiplied by 2. You don't have to do this. You don't have to memorize the formulas because it's already built in, so I could learn. You can just call it off matrix, and then you import classification report. And just like I've been doing in the previous two matrices, you start with the actuals, and then you go to your predictions, and then you get your classification report, right? So for the no cases, our precision is 80. So right, and then we have 100% recall there. This means that we've recalled all the no cases. Now for the yes cases, the most important ones, we have 0%, which means we didn't get a single case correct. 0% there as well. And then you can see that here's your accuracy. Out of 10 cases, you got 80% correct. But this is the more balanced accuracy that you want to use when you're using classification. So this one would be that plus that over 2. So F1 score for your no cases, F1 score for your yes cases, this is the average of that. And then you can see your actual accuracy is 0.44%. Now this is the accurate performance of your model. Right. Now we're going to move on to regression. So right, regression, unlike a classification, right, you use it for continuous variables, right? Your continuous variables would be time, right? So say for example, you're building a model that determines how long like a person takes to complete a particular exam. So you're gonna put in a certain set of features for that, like he's male, he's 25 years old, he wears glasses, you practice this amount of time, and then your target variable would be the time. So it's gonna vary for different people, right? Some will have like longer time, some will have a shorter time. So it's a continuous variable. So like this is the right case for classification, where your target variable probably is time. The same as money. Money can be zero amount, can be lots of money, can be negative money. So yeah, say maybe you're using regression to predict a certain individual's income. I don't know why you would do that, but like yeah, say that was your use case. You can use classification. I mean, you can use regression for that particular case, and also height, right? If you want to predict the height of people based off like say their weight, gender, and all that kind of stuff. Oh, also weight is a continuous variable while I'm speaking about weight. So yeah, the last example would be temperature, and I'm going to be doing an example off of that temperature, right? So the metrics that we're going to be looking at for regression are your mean absolute error, your mean squared error, and then your R squared. I should have included not recommended here. You will see why. Actually, I don't think I've demonstrated that one in this tutorial. I'll make a separate tutorial for that one, but I don't recommend R squared, right? Okay, cool. So now I went on the internet and then I got weather forecast for the next 8 days for Johannesburg, right? So let's say the way it's predicted, it's the way it's gonna go down. These are the maximum temperatures. So those would be our actuals. say now I have built a model, a regression model that predict that today Monday my maximum temperature is going to be 23.2 versus the actual, which is 24, right? And then along like that. So let's say now this here we've built a model and then we've run predictions, right? So what I want to do quickly before I get into the matrix, I want to visualize this data, right? Just to see how well did I do. You can see on the first day, Monday, I predicted 23.2, but it's actually 24. And going along up until day number 4, I'm close, very close to the actual there. But on day number 5, it's actually 19, but my model predicted a 30 here. So that's 19, my model predicted a 30. And I created this point on purpose to demonstrate something. I will, I will mention it when I get to the mean squared error. So, this is, so the green line here would be the regression equation that our model learned from the feature space and also the target variable, right? And then it will extract or generalize the relationship between the features and the target variable. The target variable here being temperature, and then the inputs say day of the week and wind speeds and all those nice things, right? So the relationship between the two, this is what our model picked up. But these blue points are like the actual temperatures of Johannesburg for the next 8 days, given those features, right? So this is what our model picked up. So now your mean absolute error would say for this particular day, this was the actual, and that's what my model would predict. For day number, say 6, this would be what my model predicted. That's the actual, right? So the absolute difference between those two, right, divided by the sum of all these points would give me my mean absolute error. And you don't have to remember the formula. Like I said, it's already built in scikit-learn. You just import it from matrix and then you apply it. So you get your actual weather here and then your predicted weather. So now you have 2.21. So what does this mean? It means that for every prediction that my model makes, it's going to be off by 2.2 degrees Celsius. That's what the absolute error is, right? You'll see the difference with the mean squared error. Sorry, I think this should be MSE. MSE, real quick. So yeah, now the mean squared error, it's kind of like the mean absolute error, but here you square the difference between your actual and your predicted, right? You don't have to remember that, it's already built in. So now you can see that your mean squared error, it's 16.25 degrees, right? Why is this difference so big here? Remember that I said that there's a point where I put it there on purpose. On day number 5, the actual is 19, but my model predicted a 30. So this one would be an outlier, right? At this point right over here, it's an outlier. So your mean absolute error is not affected by outliers, but your mean squared error is affected by outliers. So if you're gonna build, if you're gonna use either one of these models, one of these metrics to measure the performance of your regression model, just bear that in mind, that the mean absolute error is not affected by outliers. And then this one, you would get like a very high variation from your absolute error to your squared error because there's a presence of an outlier in your predictions. So I think, if you use both of them, that's how you pick that up, that, okay, cool, there's a point where my model went way off. So this is that indication, and then you go back to your predictions and your actuals, and then you investigate that further. So right, For R squared, I actually did not include it here, the demonstration, but I've included the link to a very detailed tutorial, like a blog, where they talk about R squared and how to calculate it and all those nice things. The reason I don't like R squared, it's because it's a coefficient of like how well does your regression formula represent your your data, right? How well does the line go through the data? But the problem with that is the more features that you add, you can add like nonsense features, the number will keep increasing to one. One which is the perfect one, zero which is no relationship between your learned your learned regression formula and the data points. I think for this one it might be 0.7 something, right? But if I add another feature that has nothing, that doesn't affect the temperature, say for example I added a feature for like, you know, for cats. So there was another column called cats, whether there's a cat present or not on that particular day, right? It's gonna increase. R squared is gonna increase and approach 1, which is kind of misleading. That's why I don't really like to use it. I'm okay with using these two, but for your Zindi challenges, they use log laws a lot. So it the theory is still the same. If you're having like a very low mean absolute error here in your model, I think yeah, you will still get like a decent score on the Zindi leaderboard, right? So just to answer the question that I started off with those guys that ask him like, okay, cool, I got 0.8, what does this mean? So if you got a 0.8 and it's a classification problem, you are optimizing to get to 1, which is 100%. And I've mentioned this before, if you get 100%, go back to your model is very wrong. Like there's something fundamentally wrong with it, so go and fix that. So you're optimizing to get close to a 1, right? But with regression problems, you're optimizing to get to 0, right? I mean, just think about it here. 0 would be this point minus that point minus that point, that point minus that point. You see, like there wouldn't be 2 here, it'd be, you know, 0.1 or something. So that is like, you know, a very good model, like a very good regression model. So yeah, I mean, this video is going over. I'm gonna cut it over here.